and it's right there, phase diagram of water, which is going to be our solvent for a lot of our reactions. And if you look very quickly, we have the most dense phase, okay, well, at least initially, because over time it'll be the liquid, but generally speaking, the most dense phase is your solid. Your least dense phase is going to be your gas, and the liquid's going to be somewhere in the middle. As we've seen in other lectures, if I start with a solid, ice, keeping pressure constant, and I go through this line here, which is a solid liquid divider or equilibrium, solid becomes a liquid, now I'm a liquid, and if I keep heating, I become a gas. And if I lower the temperature at constant pressure, I go from a gas to a liquid to a solid. All things you have certainly learned. And of course, I can increase the pressure. Okay, I can take a gas and I could increase the pressure on that gas, and I could force it to be a liquid. Now, depending on where I am, I could force it to be a liquid and then maybe into a solid. Okay, but water is unique because, water is unique because its most dense phase is liquid. So that's not going to work so much, because if you notice, this line keeps going as time goes on. Okay, as pressure increases, we become a liquid. All right, and that is the most dense phase because of the crystalline structure of the H bonding that has gaps in it in the solid phase. But in any case, what I'm talking about today is colligative properties. And colligative properties are the properties of a solution and how they differ compared to the pure solvent. So we know that water at a certain atmospheric pressure, let's just make this 1 atm. So this is going to be normal. At one atmosphere, if you look down here, this would be 100 degrees Celsius. That is its normal boiling point. And if you were to increase the pressure, its boiling point would be higher. You decrease the pressure, the boiling point is going to be lower. In fact, this line here is a air pressure curve, as we've talked about before. Now, what I'm getting to today is that this is water without any other particles or solute particles dissolved in. This is the pure solvent. So what colligative properties are is about how many of those solute particles get in the way of the solvent normally trying to vaporize, condense, liquefy, sublime for going from a solid to a gas, or deposition from a gas to a solid, or all those numbers and all those temperatures at certain pressures change as we add solute particles. And very classically, the solute particles get in the way of the solvent or add extra attractions to make it difficult for the solvent to do its normal business, or business, depending on where you live. Okay, now I just lost some things here. Now, so what I'm going to talk about today is, well, what if I was to add some solute particles? Now, solute particles are particles that interact with the solvent. So it has to be that the solute is going to interact with the solvent. It can't be a scenario where the solvent particles are not attracted. For instance, oil and water. Okay, water, of course, is that polar molecule, and it's going to have a positive end and a negative partial end, and they're going to attract, well, it could be attracting positive ions or other polar molecules. Only if there's interactions between the two do you have these effects. For instance, if you had sand and water, sand does not interact with the water, so therefore the sand does not change the boiling points, the freezing points, sublimation points. It does not. Now, how does it change these temperatures? Well, generally speaking, all colligative properties do the same thing. They all lower the vapor pressure. Now, vapor pressure, if you remember, is the force due to liquid molecules, okay, escaping into the gas phase. It's the pressure. It's really, vapor pressure is related to the rate of evaporation. If it's evaporating fast, you're producing a lot of pressure upward, okay? So what solute particles do, by getting in the way, they make it tough for the water molecules to get to the surface, and they prevent you from getting to the surface, or they're extra attractive forces that we have, that ion dipole attractive forces, okay, are extra forces that prevent the water from getting to the surface, however you want to think about it. But the amount of evaporation, okay, is now going to be lowered once you have solute particles, possibly, okay? So this line, which is really a vapor pressure line, gets lowered. So what happens here is we have vapor pressure lowering. And vapor pressure lowering, and how much it's lowered, is something called a Raoult's law. So a new triple point would be established, as if a new line here. So this vapor pressure lowering, okay, this line would drop, okay, is really equal to, or I would say related to, how many solute particles, okay, are dissolved. And the way that we relate that is something called a mole fraction. So Raoult's law, which really measures how much the vapor pressure changes in comparison to how many solute particles, is related by this formula. We have the vapor pressure of the new solvent is equal to the mole fraction of the solvent, put solvent here, which is mostly water, times the vapor pressure at standard conditions, which is based on some kind of tablature, so the pure vapor pressure. So the new, okay, vapor pressure is equal to the mole fraction times the standardized one that's based on standard conditions, that's pure, okay? And you can see that mole fraction is just that, a fraction of moles. So if we look at the mole fraction of the solvent, that's how we write it, big X. And what it means is the moles of the solvent, which most cases is the water, over the what? Total moles of the solution, which is the solvent and the solute. Okay, so for instance, if I had 100 grams of water and I had, let's say, 24 grams of NaCl. Okay, first thing I got to convert to moles. So it's 18 grams per mole for H2O. We know that because 16 plus 2 plus 2. And 100 divided by 18. And when you do that, you get 5.56 moles. And that's of water. Okay, now NaCl, 35 plus 23 is 58. I chose a good number here. 1 mole of NaCl, okay, is 0.5 moles. That's my substance being dissolved, called the solute. So total moles is by the denominator. And I can do this in my head. 1.06. It's total moles. And the moles that I care about is the solvent, which is 5.56. Okay, and it looks like I definitely made a mistake here. 6.06. Pays for me to look at it carefully. So yeah, 5.5 is 10. Yes, 6.06. I can do this. Okay, now when I do the math, 5.56 divided by 6.06, and this gives me 0.917. There's no units because the moles cancel, and that's my mole fraction of my water. Now what does that mean? That means that 91.7% of all the moles in my solution that I made is due to the water. So if I take 91.7% of the pressure at some temperature, my number is going to be lowered, obviously, because this number, as I add more stuff, is going to become a larger, smaller and smaller percentage. So add more sodium chloride, the percent of water is going to go down, and of course, a lower percentage times that value is going to give me a larger amount of vapor pressure change. So let's pretend I was to add even more sodium chloride. Let's pretend that this percentage or this mole fraction went from 0.917 to 0.5. 90% of, let's pretend that this number is 100, just to make it nice. So that would give me 0.19 times that, of course, is 9, would give me 91.7. It was 100, and now my vapor pressure's dropped to 91.7. Now, if this number now is 0.5, well, now it's now what? 0.5 times 100, now it's 50. And you can see that the new vapor pressure is what you're solving for. Mole fraction times that is going to be a larger difference from the original. The greater the mole fraction, okay, the lower your final vapor pressure is going to be. Remember, it's vapor pressure dropping. So as you add more particles, this line drops farther. Okay, and your new phase diagram looks something like this. Now, if you remember from last year, there's also another implication to this. If your boiling point was here, as I said before, well, when you put this amount of particles in it, now your new boiling point is now over here. And the difference in the temperature from these two positions is change of temperature of your boiling point. It's called boiling point elevation. And if your freezing point was here, now your new freezing point with this amount of particles is down here. You notice this little difference is going this way. It's called freezing point depression. That's a change of temperature of the freezing. And it's also colligative properties, as we talked about. But Raoult's law is simply vapor pressure lowering, which is how every single colligative property is affected. So let's go to your worksheet. Of course, this is a nice, pretty drawing of that temperature change. Here's your temperature of your boiling point. It's elevated. This line represents the drop, of course, in the vapor pressure lowering. And of course, it'll drop lower and lower as we add more particles. Here's your freezing point depression and your boiling point elevation when that drops. But we're going to look at this drop right here. So here is our homework worksheet. What is the new vapor pressure? Okay, it's going to get lowered because we're going to add solute particles in the way. If 100 grams of glucose is dissolved in 200 grams of water at 50 degrees Celsius, the vapor pressure of the water at 50 degrees Celsius is 92.5 torr. My friends in chemistry, this is the standard tablature or table data that we need. So our pressure new is going to equal the mole fraction of our water, that's our solvent, H2O, times our pressure from standard conditions, which we know is going to be 92.5 torr. So 92.5 torr. So all we need now is the mole fraction. So all you need to do is find your moles of water and your glucose. Now glucose, if you didn't know, is C6H12O6. All right, and its formula mass, if you didn't go to the formula mass party, it is 180 grams per mole. If you didn't, you figure that out. And of course, the formula mass of water is 18. These are things that you should know at this point in time of your chemistry life. So what we're going to do is we're going to convert our 200 grams of water. So 200 grams of water. I'm going to get rid of grams, so grams goes in the bottom. And I know 18 grams equals 1 mole. Set that up. And then my other one, I have 100 grams of glucose. Same idea. I'm going to get rid of grams, so it tells me when I do my conversion, grams go on the bottom. And 1 mole of glucose is 180. Let's get our calculator out. And these are the moles of each. Okay, so our mole fraction is going to be the total moles. So we're going to add these two together. Of course, we get 11.66 moles as our total. And of course, the part is the solvent goes up top. And that would go here. And it's 11.11 mole. Notice the moles cancel. A mole fraction is dimensionless unit. And what we get that the mole fraction for the water, H2O, is equal to 0.952. Okay, now we're just going to plug that value into our Raoult's formula, and we're off and running. When you multiply 0.952, which is the mole fraction of water, the solvent, times 92.5, what you get is the new vapor pressure to be 83.7. Let's round that off to 3 significant figures. I can't look at my mole fraction for significant figures because there are no units left. So this is the number I care about. It's got 3, so this of course is 3. So torr times no unit gives me torr. And you can see that the vapor pressure has been lowered to 83.7 torr. But this is, again, assuming, as I have spoken about, that our solution is ideal, right? We're assuming that the attractive forces between the sugar and the water is the same as water for water, or and sugar for sugar. Okay, that is never the case. So this is an estimate at best, but it's definitely going to get lower. And what is a change in vapor pressure? Well, if it started out to be 92.5 for the pure water, okay, now it's going to go 83.7 for the solution because the solute particles are getting in the way. Okay, I think we can handle this math. Maybe I can handle this math. Okay, so I get what, 8.8 torr is my change. What is the mole fraction of the solute? Now you could go through the math and say, okay, add these together for the total and put 0.556 on top. Or if you notice, these mole fractions have to be part of a fraction of 1. So all I have to do find the mole fraction for the solvent, I could do the math again. I could do 0.556 over 11.66, or I can just say, hey, 1 minus 0.952. Right? The difference between the 1, which would be perfect mole fraction, is that, which is 0.048, and we write like this: x of the glucose is equal to 0.048. No units. Okay, so let's continue on with the fun. In number 2, we have a glycerin, a non-volatile electrolyte. Now you say, Mr. Grodsky, what is this non-volatile non-electrolyte? Why are they saying this to me? Okay, well, they're saying it to you, as the bell rings in the background, they're saying it to you is because the non-volatile non-electrolyte tells you, number 1, that this solute, okay, does not evaporate. So if it doesn't evaporate, that means we know that that solute is going to stay in the solvent. So it does not evaporate. Non-electrolyte, okay, means that it's not going to break apart into ions. We're going to learn, if you remember, if something breaks apart into ions, then we have to calculate its effect using something called the I factor. So just saying that what we calculate it to be is as one particle. So it stays together as one particle. If it was to break apart into ions, as we see, like for instance sodium chloride, okay, that would tend to double the effect, meaning if I had a mole of sodium chloride, really I've got 2 moles of ions. And colligative property, okay, colligative means many particles. Doesn't care about what the particle is, it just basically depends upon how many. So whether your ions and molecules, if you break apart into 2 moles of ion, that's 2 particles that get in the way of water, and it will affect the vapor pressure twice as much, okay, than it would if it was just 1 mole. So that's what they're talking about there. So in any case, what we have is a non-volatile non-electrolyte with a density. Now I'm giving you a density, and density is going to pop into these types of questions because they're going to help us go from volume to mass. So they want the vapor pressure, which is the new vapor pressure of a solution, which means that we have water, and it normally at 25 degrees Celsius would have a pure vapor pressure by itself without any solute particles getting in the way of 23.8. But they want to know the vapor pressure of a solute made by adding 50 milliliters of glycine of water. So we know the formula we're going to use is the pressure nu is equal to the mole fraction of the solvent times the pressure at standard conditions, which we'll just put in right now, is 23.8 torr. So to finish this off, we just got to find the mole fraction of the solvent. So we know we have 500 milliliters of water and 50 milliliters of glycerin, which is the solute. So how do I go from volume to moles? Well, this is not a gas, so I never want to see 1 mole equals 22.4 liters. That's not what we're doing here. I see that way too much. That's for gases filling containers. So what we're going to do is we're going to take our 50.0 milliliters of our glycerin. Let's label it to make sure we know what we have. Let's label it correctly, Grodsky. And before we get to our moles, to build our mole fraction, we got to convert to a mass. And with a density, I'm going to use the density here to convert my volume to mass, as I talked about before. And the milliliter has to go down here, grams here. What we have is 1.26 grams for every 1 milliliter. That's what a gram per milliliter is. I have 1.26 grams per milliliter. And I'm going to get rid of my milliliters, and I'm left with grams. Not done, because I want to get moles here. So I'm going to get rid of grams, and I want mole. Off the top of my head, I don't know glycerin, so I know it's going to be 3 carbons. 3 times 12, 36. We have 8 hydrogens. I'm doing something called a molecular mass, or gram formula mass, however you want to think about it. Okay, 8 times 1 is 8. And then we have 3 oxygens, and 3 times the atomic mass of oxygen is 16. That's 48, and what I have is 8 and 8, 16, and 6, okay, is 24, and I have 7 and 2 is 994, so make sure I did that right. Yep, and I have 94 grams per mole, and that's my converting factor here. Alright, so you know it's 94. That's where I got it from. So I had to do a formula mass to get that, and let's go find that number. And what I get is 0.67 moles. Okay, now we're going to do it again for Wasser, or the water. Okay, so we got my water here is 500 milliliters. Since they didn't give me a density of water, I can assume that the density I can use is 1 gram per every 1 milliliter. Okay, and then of course I know that the molecular mass of water is 18 grams per mole, as I would hope most chem students at this point. 16 plus 1 plus 1. And let's go find that number. And what we get is 27.8 moles of water. Okay. And now what we're going to do is to find the mole fraction. What we're going to do is we take our total moles. Okay, so our mole fraction is going to be 27.8 plus 0.67, and I want the mole fraction of the solvent, so the water goes up top, 27.8 moles. Let's go find that number. So my mole fraction of my solvent, which is the water, is 0.97. We'll make that 6. Doesn't have a unit because the moles cancel, and that value of course goes right here. And let's solve for my new pressure. Okay, and this would be 23.2 torr. I keep the torr because this has no units. Okay, and you notice it went down a little bit, not a lot. Now why not a lot? Well, because that just wasn't a lot of moles of, I could say, not a lot of moles of solute compared to the solvent. Okay, and that's how we do those type of problems. Let's move on. Okay, and these are ones that typically give chemistry students fits at all levels, because we have, besides mole fraction, as we just learned, we have something called molarity, which we learned in other parts of the course, which is moles of let's make this a better, so molarity is equal to mole of solute, the substance being dissolvent, over liter of solution. And we also have little m, which is molality. This is molarity, this is molality, and this is moles of solute over kilogram of solvent. A little bit different. Molarity, molality, ritty, okay? So, given that, let's look at the problem. Now also percent by mass is something we've dealt with last year, but let's look at it. The commercial concentrated aqueous ammonia at 28%. So we've got 28% by mass ammonia. What does that mean? For every 100 grams of solution, 28 grams is ammonia. Okay, the density is important. This helps us go from mass to volume if we need to. They want the molarity of this solution. Okay, now molarity is big M. It's moles of solute over liter of solution. So they want to know what the concentration is. They give me a 28. They didn't tell me how much. So if they don't tell me how much, I have to make an assumption. And when you make an assumption, you make a donkey out of you and me, but we do this here. So I'm going to assume a 100-gram sample. I can assume any kind of sample I like, but I'm going to use a 100-gram sample because 28% of 100 grams is 28 grams of ammonia. So let's convert that to moles. Okay. And we know that for every 1 mole, and you say, but Mr. Grodsky, why are you converting to moles? Well, because I know that molarity, as I've written this too many times, is moles of solute over a liter of solution. So I got to get that top number. So ammonia is, what's it, 14 plus 3 is 17 grams per mole. Okay, something we should know at this point in our chemistry life. And let's go find that number. And I get 1.647, we'll say, and this is moles. Okay, that's what's going to go in the top part here. Now, problem is I need, what's the volume of my solution? I need a liter of solution. Well, if I have 100 grams of the solution, that's why 28 grams of it was NH3, how much volume does 100 grams of the solution have? And that's where the density comes into play. So I take my 100 grams of solution, which I assume, because remember, molarity is a relative figure based on how much stuff you have, how much volume you have. So is this value, percent by mass. So it doesn't matter, okay? Any case, 100 grams, and I'm going to times it by the density. I'm going to get rid of grams. Grams go in the bottom. I want the volume, which is milliliters, okay? And notice, look how I do this here. It's 0.90 grams for every 1 milliliter. Notice the grams is on the bottom because I'm trying to get rid of grams to go to volume. Now I need liters, so I have to convert this to liters. So I'm going to get rid of milliliter, and I want liter. For 1 liter, there's 1,000 milliliters. Okay, let's go find that number. So when I multiply this through, I get 0.111 liters. And now I'm going to plug it in. So my molarity is equal to my 1.647 moles over my 0.111 liter. Mole per liter is what molarity is based upon. Put this through my calculator, I get 14.84. Okay, and that's moles per liter or big M. You can write it either way. Since I'm dealing with looks like 2 significant figures, this is going to round off to about 15 big M. Okay, and that's how we did it. And let's go through the next one. Next question. Commercial aqueous nitric acid has a density, that's important, and is 16 molar. Calculate the percent of nitric acid by mass in solution. So this problem is the actual reverse of the first one. The reverse one, we started with 28%, and we're going to molarity. Here they're giving me the molarity, and I want to go to percent. So I'm going to have to make an assumption here too. I have 16 molar. To do a percent by mass, I need the mass of the part, or the mass of the HNO3, over the mass of my solution. times 100. That's what I'm going to need. So how do I go from molarity into mass? Well, somehow the density is going to help me. But the density is going to have to go from volume to grams. So I'm going to have to go from volume. So I need a volume. Does it matter what volume I have? It does not matter the volume. Okay, remember these are relative. So I'm going to assume, let's see, if it's 16 molar, okay, to get a nice value of 1 liter, I'm going to assume 1 liter of solution. Now, if I assume 1 liter, and molarity is what? Moles over liter. Hello, by assuming 1 liter, I assumed I have 16 moles of what? Remember, molarity is moles of solute. Moles of my solute is the nitric acid. So now I'm going to get my grams. So for every 1 mole of nitric acid, well, nitric acid is a 14. I'm going to do this. Nitrogen, so HNO3. So we have 3 times 16 is 48. 1N is 14, and we have 1 H. 8 and 4 is 12, 13. And I have 4 and 2 is 6, so 63 grams. Just did a quick formula mass. That's how you should be working now. I'm going to work quickly and efficiently. Okay, now get rid of my moles, and we're going to get our grams there. So I don't know why I put the multiplication sign. There it is. Let's go find our number. Okay, so this gives me 1,008 grams of HNO3. Hey, it's what I need for the percent by mass right there. Now, what's the mass of the solution? How do I do that? Well, all right, so I have the mass of the HNO3. I need the mass of the entire solution. So what I'm going to do is take the density, okay, and I know that I assumed I had 1 liter, so a liter is 1,000 milliliters. And using the density, I'm going to get the total mass. And I know that it's 1.42 grams for every milliliter, 1 milliliter. And this will give me the entire mass of my solution. Let's go find that number. And I get 1420 grams of my entire solution, which is the mass of the entire solution. So here we go, 1008 over 1420 times 100. Let's see what we get. And what I get is 70.98, or about 71% by mass of the entire solution is due to nitric acid. So 71%. So essentially 1 and 2 are just polar opposites of each other. Okay, so number 3, let's get rid of some stuff here. We have propylene glycol, sometimes used in automobile antifreeze solutions. If an aqueous solution has a mole fraction, calculate the percent by mass of glycol, percent propylene glycol by mass. So you want a percent by mass here. They want the molality. Okay, so what am I going to do here? The only information they give me was the mole fraction of the propylene glycol is 0.001. It's an aqueous solution, so that means the mole fraction of my water is something that's what? 0.999. However, I don't need the water. They want the percent propylene glycol by mass. So what I can do with this mole fraction, which is equal to 0.001, again, not knowing how much, I can make assumption. And let's review. When I only had a percent, I assumed what? I assumed 100. When I only had a molarity, and again, the reason why I assumed 100 was to make my percentage go into grams very easily. When I had a molarity, I assumed a liter to make it equal to exactly 16 moles. Well, since this is a mole fraction, why can't I assume 1 mole total? for the entire solution. That would mean I have 0.001 mole of my propylene glycol. And that would mean I have 0.999 mole of water. Can I do a percent by mass now? You bet your donkey you can. Convert to what? Convert to moles. I'm sorry, convert to grams. Remember, percent by mass is the mass of the entire solution, which would be the grams of both, over the mass of the part that I care about, which is percent propylene by mass. So once you convert to grams, you can put them through. Now, of course, percentages, you're timesing by 100. Okay, and you can look at the key to see if you get that right. Now, how do I do the molality? Molality. Well, molality, little m, I don't know what that was, doohickey. Moles of solute, which, by the way, you have because you assumed 1 mole, right? And then, of course, it's over a kilogram of solvent. Of course, you convert your mass, whatever mass you have here, convert to kilograms and find that value. Okay, and that's all you're doing there, and check your key for that. And number 4, little hints here. They want the vapor pressure water prepared by adding this many grams of glycine to water. Water is the solvent. Okay, so you're going to do a Raoult's law here. And number 5, all right, same idea here. Okay, another Raoult's law that's a little more challenging. And I would like you to go through the key there to get those questions and try your best. But if you understood 1, 2, 3, A and B, and the other 2 questions completely, then that's exactly where I want you to be at this point. Okay? Take care.